Okay, so today we're going to use our iterative processes to solve more problems in different areas of mathematics. So let's consider a problem that we would come across in trigonometry. So we want to show that 1 plus cos x over 2 sine x all squared plus 1 minus cos x over 2 sine x all squared is equal to cot squared plus a half. And hence, I want to show that alpha is a root of the equation, this equation, but I don't want to write it all out again. Actually, I'll write it out all out again. 1 plus cos x, 2 sine x, all squared, oops, that's a terrible squared, plus 1 minus cos x, 2 sine x squared equals x. We want to show that alpha is also and is a root of the equation x equals the inverse of tan square root 2 over 2x minus 1 for x between 0 and pi over 2. So we'll do that first, and then there's some extra bits to do, but we'll just do that first because the question is going to be like a slide long. So let's look at this first. So the first thing we're going to do is we're going to square the different parts of this. So we've got 1 plus cos x, 1 plus cos x, all over, so it'll be, this squared is going to be 4 sine squared x plus 1 minus cos x, 1 minus cos x, all over 4 sine squared, which comes out as 1 plus 2 cos x plus cos squared x, and then we can put this all into one fraction because it's the same down here, and that's going to be, this side is going to be plus 1 minus 2 cos x plus, the minuses cancel, cos squared x, which comes out as 1 plus cos squared x over 4, oh, it's 2, sorry, sine squared x. Oh, there's 2 of them. I'm rushing it. So we can cancel out some 2's. So we will get 1 plus cos squared x over 2 sine squared x. Now let's rewrite this as 1 over 2 sine squared x plus cos squared x over 2 sine squared x. Now this equals, what the inverse of sine is cosec, and this is cot squared x. It's always good to have all your trigonometric identities in front of you when doing things like this. Now we can rewrite cosec squared by 1 plus cot squared x. So when you see this, you see the cot, you're looking to try and get them into the same trigonomic identity. Over 2. Now this is also over 2, so what we can now do is bring this over this plus cot squared x, which I'm going to bring it over to here, which equals 1 plus 2 cot, oops, not the cos, over 2, and if we rearrange that, we will get, those two will cancel with cot squared x plus a half, which is what we were wanting. Now, I should have kept that there. Okay, we're going to now look at this and turn it into this. We'll come back to there just to kind of look at it again. So we've got cot squared x plus a half x, no, half equals x, sorry. And we're trying to, let's look back at the whole part of the question, hence show that alpha is a root of the equation, this equation, so we've shown that this is the same as this equal x is also a root of inverse tan of root 2 over 2x minus 1. So let's play with this. Let's get this as a function of cot x on its own. So cot squared x equals x minus a half. So cot x equals the square root of x minus a half. Now we know cot is inverse of tan, which is, now we can rearrange what's in here to be 2x minus 1 over 2. And we can take the inverse of this to give us tan x. So x must be the inverse tan of which was what we wanted here. So we need to find the root. Now we're going to think about if, because this is what we have from this, we derived x from cot squared x plus a half. We can find the root of this alpha, and it will also be a root of this equation here. So this is where our iterative method comes in. So let's, I might need more space. Let's do this on another sheet. So we're going to have one of those big massive tables. So we're going to let f of x equal x minus tan, the inverse tan of 2 over 2x minus 1. And so we're looking for so f of x equals 0, then what was our we were told that alpha, let's just look back to the original question for finding the root. Oh, this is a new bit of, I'll write this bit down. This is the bit that I didn't write down because, so what we now want to find is, let's actually just go to that. When I started, I didn't write the next part of the question. So, given that alpha is the only root of the equation x equals the inverse tan of 2 over 2x minus 1 for x between 0 and pi over 2, verify that alpha lies between 0.9 and 1. And using the iterative formula based on this part here, we want to find the value of alpha to 3 significant figures. So, let us so for f of x equals 0, then f of 0.9, so if it lies between these two, f of 0.9 must be 0.9 minus, the inverse of tan 2 over and we get minus 0.10685. So now f of 1 is 1 minus the inverse of tan 1 over 2 minus 1. Work that out and we get 0.44683. Therefore, a change of sign implies a root is present. Now we're going to use our iteration to find the value of alpha to 3 significant figures. So we have, so if it lies between 0.9 and 1, we're going to let x1 be 0.95. And xn plus 1 is going to be tan to the minus 1 2 over 2x to the n minus 1. And then we are going to say are they the same to 3 significant figures? So this is our x1, our x2 would be slotting 0.9 into here, working all that out, we'll get 0. I'm not going to write all that working, 0.97992. They are not correct to 3 significant figures, so the answer is no. x3 is going to be 0.96494, and again, nope, they're not. X to the power 4 is 0.97234, and no, they are not. X to the 5 is 0.96866, and again, nope. X to the 6 is 0.9 0.7048, and again no, x to the 7 is 0.9695. Now if you round it up to three significant figures, you'd get 0.970. So yes, it is. So alpha is 0.970 to three significant figures. And you can prove that it's the same by letting 0.9695 is less than alpha is less than 0. I need to do under here 9705, and then alpha would, slotting those into our formula, you get a change of sign that's very, very, very close to 0. Now, let's do another one. And this time it's going to involve area. So we've got this diagram. A line segment. This is theta. This is A, B, and C. I'm going to colour that in a wee bit, but I'll use a different colour so it shows up. A shaded bit there. Okay. So this shows a company logo, ABC. And we've got the arc of a circle of centre C. So the area of the unshaded segment is equal to the area of the shaded triangle. And theta is in radians. So firstly we want to show that theta is equal to 2 sine theta. Secondly, we want to show, I want to use an iterative formula based on the equation in A with initial value 1.85 to find theta to three significant figures. And finally, find the length AB given AC is 8 centimeters. Okay. So firstly, part A, we know the area of the unshaded area, so the area, these two areas are equal. So the area of the triangle is equal to the area of the segment. Now we know that the area of a triangle is given by half the radius sine theta. And we know from our studies of circles and such like that this segmented area is the same as half r squared theta minus sine theta. Now we can divide both sides by half r theta, so sine theta equals theta minus sine theta. And now we can rearrange this to give us theta is equal to 2 sine theta. And that's what we wanted. Now for part B, we're going to have theta, or 1, is equal to 1.85. And theta n plus 1 is going to be equal to 2 sine theta n. And then are they the same to 3 significant figures? So again, I'm not going to write all the working out. So theta 2 would be 2 sine 1.85, which gives us 1.92255. So no, I'm not going to write all these down because there's a lot of them. So theta 3 would be 1.87753, and that's no. So you keep doing all that until you get to theta 10, which is 1.89625, which was not the same to 3 significant figures as theta 9. You can trust me on that one. And theta 11 is 1.89500, which, yes, they are. If you want to do all that with your calculator, you can, but it's very tedious. So, if you let f of theta be theta minus 2 sine theta, and put this in, this value of theta into here, you would get 0. So so when theta nine, then we've got 1.895 is less than theta, and that's greater than 1.905. If you put these into the formula there, gives us minus 0.000809, and then f of 1.905 is equal to 0.01565. So you've got a change of sign, so therefore theta is equal to 1.90 to 3 significant figures. So last wee bit. Let's just get a new bit up. There's the third bit. Find the length of the arc. So let's look at this. We know that theta, we're using theta as being 1.90, sorry. So if half of theta would be 0.95. We know this is 8 centimeters, and now we have a right angled triangle. Remember, this is in radians, so we can use some simple trig. So we can use the sine of 0.95 is equal to half of a b over 8, because it's just, it's half of that. and that's then going to give us rearranging that, it's going to give us A, B is 13, and working all out 13.014, which is 13 centimetres to two significant figures. So hope that helps.